Greetings folks, welcome to this new video. In this video you're going to talk about a bit of feature engineering, then model building and model evaluation, then hyperparameter tuning, and also will include model stacking, and I guess many more things. You need to see that. So let's get into the video. So at first we are going to import our necessary libraries, obviously pandas and SNS for some visualizations, and matplotlib notebook, not in line. Okay, fine. So we have imported our data, and now let's see our data. Well, you can see our data contains age, sex, body mass index, and charges. What are these charges? Here these charges are actually how much insurance charge you need to pay when you have some certain conditions, like your age is 18, sex is female, then how much charge is you going to pay, insurance charge actually. So our goal is to build a model where we are going to predict the charges for an individual, or an individual needs to pay depending upon some of the features like age, sex, body mass condition. So we're going to see how this charge respond on different conditions of body mass index, sex, age, how they differ, how charge differ with these parameters. Okay, so let's see at first sex and female counts, male and female count. So df dot sex dot value counts, yep. So male and female are pretty close, similar. Male is a bit higher. Okay, fine. Now let's do some visualization so that we can understand our data. Okay, now we are going to use sns.catplot. Okay, now here our x is going to be what? Age of an individual, and then y is our what? You can say levels, maybe. Yeah, y is our charges, 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 and you need to specify the data. Data is our diff. Okay, let's plot it. You can see that with age, charge is increasing, linearly increasing. At the first time it's linearly increasing, and there's three different distributions. So you can say that it's not just age on which charge is dependent, there's something else which is triggering the charges, and we'll see that. I'll see that later. Okay, let's see if sex, whether there's any difference in between different sex. So hue is equal 6. Let's see that. It's taking too much time. Not a big data set. Yeah. So yeah. Ish. Now you can see that male and female are pretty close. There's no much difference. Yeah. So yeah, we'll see that actually when we will do our hypothesis test. We'll see whether there's really huge difference, significant difference in between male and female. Well, now you can change the type of the plot. It's a scatter plot. Now we're going to see a different plot, kind of, well, let's say what, box plot. Box, yeah, let's do that. Oh no, what is this? Age versus charge, female. Oh, let's do some like sex here, and hue, sex, charges. For the first time, Forget about you. Yeah, male and female, they don't have actually similar distribution. Both of them have some outliers. In the female, it's a bit more. And we'll see how we can detect outliers. Yeah, later. So female and male, here you can see male is going to pay a bit high charge than female. Yeah, let's see if there's any interference of smoking status on this charge. So here hue is going to be our what, smoke. Yes, smoker. Oh yeah, great difference. Now you can see when they are non-smoker, then both of the male and female have low charge. They are going to pay low charge, and when they are smoker, yes, this color represents their smoker. So when they're smoker, both of them are going to really pay high charges. So smoking has really high impact on our charge. Yeah. So sex versus charge. Well, smoking. Yeah. Let's see if there's any difference on region by region. Okay. So sex, charges, data, kind, hue. What's region? Region. And no, it's not going to be a box plot. We're going to do bar plot. Yeah, so you can see southwest, who is this yellow? Southwest. Yeah, in both cases, both sex groups, females and males, people who are living in the southwest side, they're paying high charges. Yep. And this northwest is going to pay low charges. It seems like they're racist, or maybe not. Okay, we're going to see a bit more on region. df dot group by, we're going to group our data by region. Group by region, and we want our output on charges. So dot, let's say mean values. Let's see that. Oh no, df dot group by region charges. That's the problem. Group group by. Yep. Now you can see the values. You can sort it. Dot sort sort values by what? By, sorry, no by, sort values ascending as well. False. Yep. Now you can see. Yep. Southeast, isn't it? Yep. Southeast is going to pay high charge. So 14,000, 13, 12. You can plot it also. Dot plot plot kind equal what, bar, yeah, comma quotation. And as we are using a notebook matplotlib, so you need to say plt dot figure. Okay. Yep. Now you can see that. No, that's not much difference. 2000, not 2000, 1000. Yeah. Well, let's see what body mass index and charge, which I think will have larger impact on charges. So SNS dot cat plot, or you can do LM plot. Now our X is going to be body mass index, so BMI and Y. And Y is what? Y is charges, CHARGS, charges. Now the data frame is df, and let's plot it. Yep. So now you can see clearly that body mass index and charges have really a relationship, but it's not a very good relationship. Lots of outliers, and majority of them are here in this region when the body mass index is 30, 35, 20, 25 to 35 in this region, majority of data, and all of them are with low charge value. Now let's say I wanna plot it for when the body mass index is just 30, greater than 30. Okay, so how can I do that? So let's say, well, before that, let's add hue, sex. Hue equals smoker, not sex. Smoker. Now you can see smoking has significant impact on body mass index versus charge relationship. When the individual is a smoker, then you can see quite a good relationship. And for the non-smoker, it's not a good linear relationship. That's poor relationship. But when he's a smoker, or he or she is a smoker, then this is quite good linear relationship. Okay, fine. Let's see, we wanna plot it for when the body mass index is above 30. So how can I do that? We know how to filter our data, and now we are going to apply that method here. So data is not just df, we want data for what? When the body mass index BMI is greater than what? Body mass index is greater than 30, let's say. Okay, so we have filtered our data and now plot it. Now, one valuable insight that you can get from this plot is that body mass index doesn't have any good relationship with charges if he is not a smoker. Okay, now you can see that here, that if the subject is not a smoker, then body mass index and charge, they don't have any good correlation. But when he or she is a smoker, then there's a really good relationship, linear relationship. So yeah, that's, I think, a good plot. So now let's head over to hypothesis testing. Okay, hypothesis test. Okay, heading hypothesis. Well, now our first hypothesis is, let's say we want to know, do the charges paid by female significantly differ from the male? So here our null hypothesis is like they don't have any relation, they don't differ significantly, and while on the other hand alternate hypothesis is, yes, they differ significantly. So there's a statistical significance. So to do that, at first you need to segregate our data. You need to make two new data frame. One is for female and another is for male. So now let's say female is equal to df.lc. Now what? df when sex is equal female. Okay, so let's see what it returns. At first I'm not going to store it. So it's just going to return us the data set for female. You can see sex, female, but we don't want all the columns, sorry. We want just this charge column for females. So you can do that dot chargs charges. Now you can see all the other columns are gone. The same thing you can do by, that's another way of doing that, a comma, then a quotation, charges. Now you can see same thing. and now we're going to store it in female. Okay, so similarly you need to make another column for male, and for male you need to just change it to female to male. That's it. Now SciPy provides us pretty handy libraries to test our hypothesis. Okay, now we are going to import our SciPy library. From SciPy we are going to import t-test, and right now we are going to do a t-test. We can do t-test, z-test, and over many there's many tests, so that's actually another topic to discuss about. I'm just going to briefly talk about this t-test and maybe z-test also. So we have imported it. Now task is what, and then we are just now going to pass our two datas, male and female, and this t-test int function is going to figure out by its own other things. So male, female, and what, that's another argument. Equal var, that is variance. Do they have equal variance? No, they don't have equal variance. You can also inspect that. I'm just going to say QL equal var equal false. Fine. So let's see what it returns us. So it returns us a t statistic 2.18 and one p-value, and this p-value is less than 0.05, so we can reject our null hypothesis and accept our alternate hypothesis, that is they do differ significantly. So you can say that the charges paid by male do differ from female statistically significantly. Alright, now let's see one z-test, and that is actually there's nothing to do with the charges column. It's now we are just, let's say we want to know, is there any difference or there is statistically significant difference in between the proportion of smokers in different genders. Let's say, so what I mean is that I want to know, does the number of female smokers significantly differs from the number of male smokers in this dataset. So at first we need to do what? We need to segregate our data as we did for the previous one. So here we need to know the number of females in our dataset. So now you can see that value counts. You can see female 662, total number of female in our dataset. So we want to grab that. How can I collect it? It's in the index number 1. Okay, now you can see just 662. Fine. So it's number of female. Now for the number of male, I need to do a little bit of change, 0. Yep, now you can see number of males. Sorry, yes, it's 676. Yeah, so now we want to know from those 676 male samples, how many males are smoker. Alright, so how can I do that? It's like this, same previous one. Copy that, paste it, df.loc, and what, df.sex equal what, male, and we want our output on smoker. dot values count, just see what it returns. Yep, you can see yes or no. For males, yes is 159. So out of 600 and what, I don't know. So let's say out of 600 samples, 159 males are smoker, and so it's in the position of what, 1. Okay, let's see the same thing for female. How many females are smoker? Sex is female. Fe, female. So it's 115. Well, now that we know the proportion of or number of males or female smoker, now it's time to run the proportion z-test. Fine. So to do that, you need to import proportion z-test from stats model. And here what we are passing is number of males and females that are smoker. So here 115 female smoker, and this is male smoker, and here the total number of females and males respectively. Well, now we're going to run it. The values it's going to return is, one is z-test value and another is our p-value. So our p-value is less than 0.05, so we can reject our null hypothesis and accept alternate one. That is, yes, the proportion of male and female smoker do vary significantly, or statistically it's the result is significant. Fine, so I think that's all about hypothesis testing in this video. Maybe I'll make another video on that alone. So now we are going to talk about outliers. Outliers are actually some of the abnormal values in our data set, and there's a number of ways to detect outliers, and we're going to be talking about what quantile interquartile method. Okay, so at first you're going to see percentile, some percentiles. So what does 25th percentile, 75th percentile mean actually? So let's say df dot age dot quantile, sorry, QANTIL quantile, isn't it 25th? Yep. So the 25th quantile, that is 25th percentile, the age, 25% of our samples age is below 27, and if you write here, let's say 0.75, that is 75th percentile, that means 75% of our samples age is less than 51. And now if we see this, we are going to look at this percentile using a box plot. Then I'm just going to import my box plot. Then box plot is I'm recording it. Box plot age. Now here you can see that, yep, 27. This is our 25th percentile, and or you can say quantile 1, and this is our 75th percentile, this upper one, or you can say quantile 3, Q3. So here this is Q3, and if you write what 25th percentile, then it's called quantile 1 in box plot Q1. And the difference between them, that is what Q3 minus Q1, is known as interquartile range, IQR. So yep, interquartile range, yes. So in this graph you can see that, so that 51 minus 27 represents the interquartile range, and the way of detecting outlier is, alright, now the values that goes 1.5 times interquartile range from this third quantile or those values which goes below 1.5 times interquartile range from this first quantile are known as outliers. So now the rule for that is just like that. So now you're going to actually set some limits, and one upper limit and one lower limit. And the upper limit is the values that goes 1.5 times the interquartile range. From what? From this third quantile. And for the lower limit, we're going to say just Q1 minus 1.5 multiplied by interquartile range. So this is our upper limit, and this is our lower limit. Okay, well, now it's time to print those outliers out. So to do that, we're just going to df in a bracket, square bracket, going to pass df dot age. We're going to extract those values less than our lower limit, and or not and, so that's why this pipe operator, and or df dot age greater than upper limit. So this will return us all the outliers for just this age column up. So we got no outlier in this age column. Now to make it a bit easier, so for all the columns we are just now going to write one function here. So here quanta, everything is just as like before. So what you're doing, just writing a function, x is age, or now here you can specify x as any column name. Now outlier, outlier, let's say for which column now you want to see outliers. Let's say BMI. Number of outliers is 9, and these are the all outliers. Here for body mass index 49, 48, and if you would like to remove them, so just you need to just put what, that's symbol. You will see those values except outliers. Now we can also do that for our charge column, that is which is our what, our target column, and number of outliers. Oh. Here we got 139 outliers. Too much this is. So if now we delete all those 139 outliers for our charges column, it will also delete our some of the good rows from age column, sex column, body mass index column, because they don't have that much outliers. So deleting all those outliers is always not actually a good choice. So we can actually keep those 139 outliers. Alright, so far we have done what? We have done some of the visualizations to inspect our data, then what? Then we have done some hypothesis testing, and finally outliers. We saw how to detect outliers. Obviously there are some other ways to detect outliers. One is standard deviation way. Well, so far we have talked about hypothesis testing, data visualization, outliers detection, and now we are going to talk about correlation. And correlation analysis is really simple in Python. Actually, you just need to do df.corr correlation. Yep, and by default it's Pearson correlation, and you can change that also. Here you can see method is Pearson, so to change that you need to write method equal Kendall or Spearman, what you would like. Okay, one thing to notice here is that we got our sex column, region column, but those are not here because those are actually categorical features, and as they are not what, they are not numbers, continuous numbers, in correlation you don't see them. So to do that, we need to convert them into dummy variables, and we'll see that in a minute actually. So let's make actually a heat map of this correlation. Fine, you can see now that what children, no children, not highest correlation, higher 0.3 charge with age has high correlation. Now charge with BMI is 0.2 just correlation. Okay, let's see them later in more detail. Now this part is actually redundant, we don't need them. So to remove them, we are now going to just modify a bit. Now we are going to see core plot. Our data is diff. Now you can see a beautiful plot, correlation plot in front of us, which is actually devoid of that redundant part. Well, now to see the correlations for all of the features, we need to convert our categorical features into dummy features, and before that I want to modify our features a bit, because as we saw in the earlier video that right in this plot we saw when body mass index is greater than 30, then they need to pay a high charge. And with that in mind, we're going to modify our data set a bit. So now what we're going to do is that we are writing a function when body mass index is greater than 30 and he or she is a smoker, and return fat smoker, and else everything is normal. It doesn't impact significantly the charge. Okay, now we are applying that function to our those two columns, body mass index and smoker, as you need to pass two columns. That's why this lambda function, and that this way. Okay, now yes, okay, fine. Now you can see one new column, fit fat. When the body mass index is less than 30, here 27, then it's normal. Okay, so everything is fine. Now we can run our own hot encoding or get our dummies. Now as this region is going to generate some of the dummy features, maybe 3 new features, I'm just going to drop it to avoid complexity. So df dot drop, you can keep it if you want, drop region regi1, and what in place equal true, so wouldn't have to reassign it to a new variable. In place true and x is equal 1. Okay, let's do that. Oh, in place, yep. Now let's see our data frame. Oh, we don't have any. What is that? Was that region? Now we're going to pass pd dot get dummies. Pd dot get dummies. You need to pass df our data frame and drop first. We are going to drop one redundant column from those dummies. Actually, yep. Let's see that what it returns. Sex, male, smoker, yes. If he's a smoker, then it's 1. If it's a non-smoker, then 0. If he's a male, then 1. If it's female, then 0. That's it. Pretty simple. And fit fat, if it's fat normal, then 1, and if abnormal, then 0. Okay. And we are now going to store it in a new variable df2. Okay, now we are going to run our correlation plot again. core plot plot and our diff. Oh no, what is it? Diff 2. Okay, now you can see some changes and one high value here, 0.79. Charge with which smoker is, yes, that's pretty obvious. If he or she is a smoker, then he need to pay a high charge. And other thing is, yes, negative correlation here, fat normal, and what is it? I can see that. So okay, diff correlation, diff 2.0 double. Yeah, now you can see charges. Well, I can also do one thing, charges. Yep, now every correlation you see here is with charge. So age and charge 0.299, that is 0.3, moderate correlation you can say. But with smoker it got really high correlation, and fit fat normal, negative correlation. That means if he is abnormal, that is fat, then we'll get really high correlation. Yeah, if normal, then negative correlation, it's okay. The results we got from this modification seems to be pretty fascinating, but there's one more thing we need to test before we feed this data into our model, which is known as multicollinearity. Right here you can see that when smoker is yes and fit fat normal, then they have pretty high correlation, and this is bad when you are going to use a regression model, because when independent features are correlated, the regression model doesn't work well. So for that there's a test known as variance inflation factor, and we are now going to see that. Alright, so here what you need to do is you need to import variance inflation factor class from stats model, and here just a bit of simple codes. Okay, let's run it, and we can see here our features and test score. And there's a rule of thumb that features with score values greater than 10, you can drop them, or better to drop. So you can see here fit fat normal and age. I don't think there's any problem in age, and BMI, body mass index, has higher score, so we can drop one of them. Well, now the question is which one to drop, and the answer is pretty reasonable, because we are going to keep that feature which has highest or comparatively higher correlation with our target variable. So right here you can see that fit fat normal has comparatively higher correlation with charges than the body mass index column, so definitely we'll keep fit fat normal. So but I'm not going to drop that right now, because that we'll see in our next video, how we are going to build our model and see if that has any impact on the accuracy of our model. And up next we'll see, I think, a lot more than that. Hey guys, welcome again. Earlier in this video we saw some of the basic data pre-processing steps that are required before you feed your data into a model. Now we're going to see how to build a model and compare different models and see the best one. Okay, so again we are just importing our data as a fresh one and dropping that region column. Then we are getting all those dummies, and we are not doing any new feature engineering, like we're not making any new features. So just see how this turns out. And here is our X is our training, not actually training, these are features, independent features, and Y is our level or dependent feature, which is we are interested in which we are interested in, we want to predict those charges. Now if you see the X, you can see X is just all those features except charge. Okay, now let's pre-process our data, because if you don't pre-process, min-max scale your data. If all the data are not at the same scale, then your model will be biased. It will put higher weight on one particular feature, and that is bad for our model. So we have imported this min-max scalar class and transformed our data and stored it into new variable x2. Fine. And now the time is to feed our data into the model. Okay, here we have imported this linear regression class and made this linear regression object, LR object, then feed the data into the model. So this is our x2 independent features and y our level. And at first we are not going to do any test on it, so just one single data set. Fine. Then we're predicting it. Y hat is just our predicted values, and we're going to now see the score model performance, and this is just R squared value, or R squared value 1 means this is perfect model, and the less R squared value is, it's not that appropriate, not accurate. So let's see what it is. So it's just 0.74%, we can say. Let's see some other metrics also. Here you can see root mean squared error. That means which is 6056. So we may go $6,000 far from what we predicted. Far less or more. Okay. Now let's see our model coefficients. That is our model parameters. So you can see some coefficients, but you don't know what coefficient belongs what feature. So to do that, just made a little this code. So now you can see age versus weight, BMI versus weight. So, and we can see that maybe what 11,000. This is smoker 23. Yep, so smoker is got the highest weight. That means our model is highly correlated with this smoker feature. This has highest impact on our model, this feature has. So you can also make this a data frame. Now you can see in a bit fancy style. So coefficient versus feature. Okay. And now here is also sorted by coefficient. So you can see smoker got highest weight. And let's compare our predicted value and the true value. So Y is our true value. Let's see 5 charges. First 5. You can see first one is 16,000. And let's see our predicted one. What it predicted. It predicted that 25,000. And second one is just 1,075. 70. 1,000. We predicted that 3,000. Okay. We can also make that a data frame. So let's just see our data frame, actual versus predicted. Actual, predicted. So I think there's a lot more we can do to improve our model performance. Let's see how we can do that. One thing is that it's good to see the skewness of data. Is our data is normally distributed or not? Because it's good if in case of linear regression, If your data is normally distributed, then it's better. So to do that, what you can do is df.skew. Let's see the skewness, and skewness of 0.78 is, I guess, yeah, acceptable. So you can see, okay, children a bit skewed, 0.9, charges more skewed, smoker is 1.14. We can also plot them, but I'm not going to do that right now. So let's transform our model, our features, so that it may look like a bit normal. So to do that, we are going to just do log transformation. Log transformation. Let's do that. And notice here we are doing np.log 1p. 1p, that means log 1 plus log plus 1. Because if you just give here log, then here we have some zero values, and that will return us some errors. Okay, that's why log 1p. Okay, let's run it again. And numpy, import numpy as np. Okay, now it's okay. Now let's earlier it was 74, now it's 76. Okay, let's see, it's 44. Oh, it's now in log scale. Now let's see our coefficients. 0, 0, what are those things? So this is not satisfactory. 0, 0 coefficients, I don't know why. Okay, now let's do one new thing, that is we have done earlier, that feature engineering. Okay, now let's see if we again create two new features that we have seen earlier, then how our model is going to change. Okay, so now I'm going to do a fresh one, again importing our data and creating two features as we saw earlier, fat smoker or normal. Okay, let's run it, and we have also scaled our data. Let's see the score, R-squared score. Earlier it was 76, I think. Okay, now you can see a significant improvement, 86. It's really huge, from 76 to 86, 10% improvement, huge one. And also see our prediction versus true. Actual 16,000, predicted pretty close, 17, 44,000. No, 4,000. 21,000 versus 5,000. It's big difference, I think. 21 versus 55. It's really huge difference. 3, 5. Okay, let's plot our predicted versus true, and here's a little bit of code to do so. Okay, what happened? Y train is not okay. Oh, we haven't done that yet. Y hat. Okay. Now you can see the plot is now clear to you. Fine. But here there's a huge difference. Again, okay. What is it? Oh shit. Again, huge. So let's see what are the causes for this third indexed value. Why is that so different? That is so different. Again, let's see our df. And if you see 3, here you can see age 33. Okay, BMI 22. So it's okay. BMI is fine. Children 0, but charges huge. Sex male. Smoker, non-smoker Oh no, he's not a smoker, BMI is less than 25, and still his charge is pretty high. So now we are going to see if a person is non-smoker and BMI is less than 25, then for them what is average um, charge. Okay, now again you need to input our data because our data is now a bit modified. So let's see that if he's a smoker, non-smoker, and BMI is less than 25, these are their charges. And let's see the mean and mean charge is just 7,500. That's pretty low compared to that 21,000. Yep. Now let's quantile. Quantile, how is that spelled? Quantile, okay, maybe. Yep. So quantile 90%. No, 0.9. Yep. 13,000. So 90% of them are having charges below 13,000. Let's see, 92%. 14,000. Okay, we can say that 15,000. Now let's see how many of them are having charge greater than 15,000. And that is, I would say, without a doubt, their outlier in our dataset. So we are going to drop them. Now what we are going to do, I'm going to charge and as that and charges is greater than 15,000. Okay, and now close that bracket. Name changes, charges is not defined. df.charges. Yep, now you can see all of them are non-smoker and body mass index less than 25, but charge is more than 15,000, and they are just 8%, less than 8% of that portion of our dataset. And we are going to delete all of them. So how many of them here? Maybe 10. Okay. Now to drop them, we can see what dot index. See their index. Oh, what index object is not called. Okay, now I think I got it. It's just this. It's an attribute. Index. Oh, what happened? Yep, fine. So these are all the indexes where our charges greater than 15,000, and now you're going to drop them. So df equal df dot drop index equal just all of them. Control C, Control V. Okay. And we are now going to reset that index because some of the index are not now just missing. Reset index. Okay, let's see our df again. Yep, now the third one, that was 21,000, but that's just dropped. And this is now we are going to apply on what? Yep, here. Apply here. Yes, Control V. So let's see that again. 87. Earlier that was 86, now it's 87, and yeah, a bit improvement. Actual versus predicted 16,000. Okay, plot it. That's more. Yeah, now it's a bit reasonable. I can also plot more, not just 10, just let's say 100. Yep, it's working good. Seems good. Okay, so far we have been using just the whole data set to train our model, and we are not testing our model. Now we are going to split our data into training and testing portions, and then at first run our model in training data set, then test our model on that holdout testing set. Well, now before we get into the train test section, I wanna say that we are not talking about any of the mathematics behind these models. I mean, how cost function, gradient descent, etc. works. So I would say that you can check that out. Check out this model, this machine learning model by Andrew, and this is totally free course from Coursera, and here you may know all those things, how cost function work, then gradient descent works, how automatically we update our parameters W and B. So I would say, yeah, it's really essential for you. Though they taught this course in MATLAB or Octave, but that doesn't matter. You just need theoretical knowledge. Okay, so again back to our Python Jupyter Notebook. Well, now we are going to train our dataset app, training and testing dataset. So here we have imported this train test split from scalar, and making this xtrain xtest data portion from this x and y our data. So here test size is pointed to mean we are going to hold 20% of our data. 20% of our data we are going to use to see the performance of our model on unseen data. So by this way we can know whether our model is overfitting or underfitting. Okay, so we are again scaling our data. Okay, then transformed it. Let's run it. Okay, and again the same thing. Oh, now you can see it's 88%. R squared value is 88. So it's 7 on test. So train test pretty close. Training 88, testing 87. I would say yeah, your model is performing well. Okay, now so far we are doing just working with this linear regression, simplest linear regression model, ordinary linear regression. Now there's some other ways to build a regression model, that is ridge regression, lasso, elastic net. You can also use tree-based models like random forest, XGBoost. So let's see some of them now. Okay, before that, let's see some other metrics also. Yeah, training set, root mean squared error, it's now down to 4,100, and at first it was 6,000. Maybe we can lower it a bit by just removing some of other outliers from our dataset, and we can detect outliers from this graph also. Yep, this is true versus predicted one. Red one is true and this blue one is predicted. I think yeah, it's fine, but here is a bit problem in this index number 50. Now here you can see that our predicted was just 8,000, while true value was 24,000. Maybe we can inspect that. Why is that discrepancy? Alright, let's now start with ridge linear regression. Okay, so in ridge linear regression, there's a parameter you can fine tune, that is alpha, and by default this alpha parameter is set to 1. Okay, this is set to just 1, and this regularization parameter is known as, I think, L1 L1 penalty, I think. Yep. So this is 88 on X train, and if we see that on test set, it's 87. So they're pretty close. Fine. Now let's change the alpha a little bit. So let's say 1.5 alpha. So it doesn't change the bit. Let's say 15. Okay. 86. Okay, you can play with different values. Now let's do that for alpha. Will be alpha equal range. We are going to start with the range of values. Let's say 1 to 30. Now if you would like to start with fraction, you can use linspace function. Okay, np.linspace. Now alpha equal, okay, for let's say I in range, for I in alpha. Now you're going to build our model. Model equal what? Let's reach this range. I'm just good at copy pasting. Okay, yeah, you don't need it. Yep, alpha equal our I. Okay. Now we're going to see the score. So model dot score what? Model dot score. Sorry. Oh, we need to feed our model at first. Reach, then model dot fit. Yep. So model dot fit x squared y squared model dot score. Now I would like to plot the score for different scores for different ridge alpha values. So to do that, we need to store our score in a variable score, let's say. So score dot append this model score. Okay, now at first just print our score. SCOI. Yep, now you can see for different alpha values, that is here I, which ranges from 1 to 30, I got different scores. 88, 87, 87, 86. Seems like default one was good in that case. Okay, now to plot that, what you can do, plt dot plot, I guess, yeah. And x is what? X is our, I guess, alpha, and y is our what, the score. Yep. Now you can see when alpha was 0 or 1, accuracy was highest. Then it dropped. Okay. With increasing alpha. Now what? Let's also try for test set score dot append. Now for that we are going to write another score variable for test set. So score 2 dot append just this thing score. What I'm doing, Control C, but append model dot score xtrain, so it should be xtest and ytest. Okay, so score 1, score 2. Okay, now plot it. Plt dot plot alpha versus now score 2, and go to legend, plt dot legend. Okay, for the first one it's train. For the second one it's test. Okay, now you can see training versus testing outputs for different k, alpha. You can also write the levels. Okay, now you can see that seems like there is no alpha value, or training and testing results are going to merge. So our model is a bit overfitting, I guess. But the difference is not so high, 88 versus 87. Okay, so I would say, yeah, the default one was better. That is, you can also use a list, list of values. Let's say 0.1, 0.3, etc., etc. Then see again. Yeah, 87, 88. No significant change. Fine. So let's see k nearest neighbor, how that perform depending upon different k, that is what kernel. So that it's training and testing 5. When the k value is 5, I guess, yeah, or here, yeah, that time, or you can say here k value is 25, testing value is around 85, training is also that time around 85, maybe at 25, 20 is okay in that case. Okay, now what you can see again is that you can change this, let's say seed 1330. Now see this linear regression. Previously it was what? I didn't track that. But let's see if the reach or lasso has any change. 86 versus 88. Now testing set has higher accuracy. Let's do that. What? No. Oh. Plt dot figure. Yeah. So now they are far apart now, I guess. Training is a bit down, testing is up. Let's see for k nearest neighbor. Oh, it's now fine when the k is 10. Training and testing, both of them are giving us same result. So for k nearest neighbor regression, we can say that when k is around 11, then this is going to be really a good one, and it's what? Let's see the accuracy value. Here it is 88. Yeah, good for both of them, training and testing. So now you can see that by just changing the alpha value, the random state value, our model performance do intend to change significantly sometimes. So it's because actually we are now using different training and testing data sets, by just changing this random state. So rather than relying on just one single training and testing splits, we can now build or run more than one model on different training and testing splits. And that's why we use what's cross-validation. Okay, here is our cross-validation. So at first you have to import this cross-val score class. Then cross-val score, then here RG, this is our model name, any model name you can give. Here RG is our reach model name. Where is it? Yep, reach, RG reach. You can pass your LR, that is linear regression model name, or anything you want. Here X2 is our just whole data set. As you saw earlier, you can see here. Where is it? X2, yeah, here, scaled data, whole data. We have not splitted it into training or testing. Okay, and this Y is our level, and CV is cross validation. How many validation or splits we want in our data set. So we are using 5. And scoring is R2, that is R squared. And one thing to note here is that CV5, that means we are now splitting our dataset into 5 equal portions, and at the first model that we are going to run a total of 5 models, and at the first model we are going to use the first set to test our model and remaining 4 sets to train our model. And then in the second model, we are going to use the second set to test our model, and remaining 4, that is 75% of the data, to train our model. Okay, so run that. Now you can see 92, huge, 79, 90, 86, 88. So you can also see CV scores dot mean. Yep, average 87%. 87. That's a really good one. Not bad. You can do that for some other models also. Okay, now let's see one tree-based model, that is random forest regressor. So here we are using this random forest regressor. Number of estimators 1000 and maximum depth 3. So these are some of the fine-tuning parameters, and random forest or tree-based models use a lot of parameters. Okay, so let's run this model, and you'll see it will take some time compared to others. It will take longer time. Yep. So 86 versus 87, fine. Now we can play around it just by changing this number of estimators, maximum depth, and it takes many other parameters also. You can see that just by holding shift and tab. You can see what other parameters it takes. And there's also a trade-off actually in between number of estimators, maximum depth, let's say learning rate. Okay, now so to find out the best parameters, we use grid search, so that we don't need to manually set them and apply one by one to see which one is going to give us best outcome. So now you're going to use this grid search method. Okay, uncomment it. Then what we are doing here is just we are importing this grid search CV what class, and then K4 for this what cross validation, and robust scalar, it's another scaling method. Okay, at first we have scaled our data, then K4 we have 5-fold shuffle. Yes, we shuffled our data. Okay, model gradient boosting, now you're going to use gradient boosting, and you're going to experiment with just 3 different parameters: number of estimators, learning rate, and maximum depth. If your learning rate is too small, then it will take huge time to finish the model, okay, or to converge the point. So let's run it, but I'm not going to run it because it will take so much time. And I just run it, and we saw the one thing to say, that we have created this grid search class, grid search object, and it takes this model parameter, that is our model gradient boosting regression. The parameter grid is as previous one, we saw that actually earlier in this dictionary. Then CB, we can just pass here 510, but we just did some work here. Scoring negative mean squared error, we don't have any root mean squared error, that's why we're using the closest one, negative mean squared error. Number of jobs -1. Okay, then fitted the data, and best GB best means best estimator. Here this variable is going to store the model when the estimator, on which estimator our model is going to best perform. Okay, now np.square root, we are square rooting the score because it's squared error. By square rooting it, we will have root mean squared error. Okay, now we can see the GB based. Now you can see learning rate 0.01, maximum depth 2, number of estimators 1000, and loss is 4200. And for what? For let's see now reach, lasso, and others. Now similarly we can run lasso for different alpha parameter, alpha value. Okay, now you can see 4200, pretty similar to gradient boosting. Then K nearest, how is reach? Yep, here is reach, lasso. In lasso it's 0.02, 0.02 to 0.03. I saw that last time maybe. Yeah, but it was 0.03. Neighbor 515. Wow, huge. Okay. Now that we have run multiple models, we can compare them, which one best perform on our data. And to do that, we have one simple way here. You can just indicate, or I could say select the best one from these models, this grid search, or by visualizing them, what I have done here actually. Here we have used CV4 number 4 10 folds I have used. Okay, negative mean squared error. Then RMS dot steady. Oh, yeah, np dot square root. Yeah, guys, it's in square root. Okay, let's run it. This is our normal ordinary one, 4100. Then bridge, lasso, Canon, and gradient boosting, and lowest standard deviation in the case of Canon. But in the case of Canon, our loss is high, 4400, around 500. Okay. Now let's plot them, different algorithms versus their loss. And you can say that lasso, reach, these three are okay, fine, and gradient boosting is not that good, I might say. Also Canon, but you can play with experiment with XGB boost or support vector machine. Maybe we may find out something more robust or what, polynomial. Okay, now you can select one of them either, or you can stack all of those models to build one robust supermodel actually. So now we are going to do that. Actually, we are going to stack all of them and see the output. So to do that, you need to import this stacking civil regressor from Analytics.m. So you need to at first install it. Okay, then let's see the loss. Oh, 3800, significantly low, it's low loss, significant improvement, because earlier you saw none of them was below 4000, but this time this stacking process has given us 3800. It reduced the loss by, I would say, around 300. That's impressive, I would say. Yeah. And finally, you can use another one, that is model blending. I found sometimes it's more effective, more robust than the stacking one, but sometimes not. You just need to experiment with a lot, with different weight, and the sum of the all weights will be 1. Okay, so here you can see the loss is 4178, which is not pretty bad. I'd say are good compared to independent one, 4161. It's 178. Okay, it's a bit high. Well, now finally we can plot them also, our last prediction. So you can say they're pretty close, so you can say yeah, it's doing pretty good. Fine. Oh, one last thing to mention, I actually forgot to mention that, is residual. It's nothing but just you need to subtract predicted values from the original true value. That's it. Then you can see the distribution of that residual. If they are normally distributed, then okay, fine, that's good. And you can also see the trend of the distribution of that residual with predicted one. So that's it for now. I hope you find this video helpful. If you have any questions or anything to say, you can write that in the comment section down below, and hope to see you in the next video. Fine, thank you.